We were supposed to meet on Monday, but as some of you are aware, those of you who probably tried to log on Monday couldn't because I was coming from somewhere by that particular time, so I was still on the way, so we couldn't meet. So I'm requesting and also suggesting at the same time that we use the link the link for the makeup class on Saturday, so that we could do a catch up, because you have to remember that we have a quiz next week on Friday, I believe. So I'm suggesting a makeup class to replace the one we missed on Monday on Saturday. I don't know what people's conclusions are, thoughts are on that bit. That way, we are going to have at least 3 lectures to cover the other bits, the lecture 8 notes. It will also put you in a much better position to do your quiz, because I think if some of you have paid attention to what's happening on Moodle, your quiz is going to be for 1 hour. So it might be, you might have more questions, most likely you're going to have more questions than you have had before. So are we in agreement that we should have a makeup class on Saturday morning at 9 hours?
Yes, sir.
Okay. With that being settled, we can move on to what we need to look at. So, as part of our studies of circular motion...
Yes, sir.
Alright, thank you very much. So as part of our studies of circular motion, this morning we want to look at something called centripetal acceleration and centripetal force. Now, so far, our discussion, every time we have talked about acceleration, our acceleration has involved a change in velocity, as in the size of the velocity has changed. For example, if an object was moving at 5 meters per second, then the velocity of this object, which was moving at 5 meters per second, changes from 5 meters per second to 10 meters per second or 12 meters per second in 3 seconds, stuff like that. Or if an object was rotating at, let's say, maybe 7.5 radians per second, then it starts to rotate faster. It changes to, let's say, 15 radians per second in a certain amount of seconds. So basically what I'm trying to say is that so far our discussion of acceleration has been primarily concerned with the change in magnitude of the velocity, or a change in magnitude of the angular velocity. That is what our acceleration has been. Discussion, when we talk about acceleration, it has all been about change in how fast is the magnitude of the velocity changing. However, you can also talk about acceleration in terms of direction. The magnitude can remain the same. Are we clear? The magnitude can remain the same, but if the magnitude of the velocity is the same, for example, you are moving with a velocity of 10 meters per second, and this 10 meters per second velocity does not change, it stays 10 meters per second, but the direction of the velocity vector changes. If the direction of the velocity vector changes, then it means that you're no longer talking about the same velocity, because velocity is a vector. Velocity is made up of magnitude. Velocity is made up of direction. So if the magnitude changes, or if the direction changes, or if both of them change, then what you have is acceleration. Are we clear? When we talk about velocity, velocity is a vector. We can talk about acceleration in terms of a change in the magnitude of the velocity. But it's also possible to talk about acceleration in terms of a change in direction. Now, one case, when we talk about centripetal acceleration and centripetal force, we are talking about an object whose velocity magnitude is the same, but the direction is changing. The direction in which the object is moving keeps on changing. And this is a case when an object is moving in a circle. When an object is moving in a circle, the direction of that particular object moving in a circle just a minute. All right. So like I was saying, we want to look at how much change in velocity happens when an object is moving in a circle. Because as an object is moving in a circle, for example, if you look at a car or a bus going around a roundabout, the direction in which the car or the bus is pointing changes constantly as it goes around the roundabout, despite the fact that this particular vehicle is moving at the same speed as it goes around the roundabout. Because usually people tend to move, I think people with a sense of physics, they tend to drive at the same speed as you go around the roundabout. You don't increase or you don't reduce your speed in a roundabout. You drive at the same speed. So the velocity, the size of the velocity is the same. But what is changing as you go around the roundabout is the direction. The direction in which you're moving changes. So if one part of this particular vector, if this velocity, if the magnitude stays the same, but the direction changes, then you are talking about acceleration. And this kind of acceleration, which happens when an object is moving in a circle, this is what is referred to as centripetal acceleration. From our discussion about Newton's second law of motion, we know that whenever there is a certain kind of acceleration happening, from Newton's second law of motion, we know that whenever there is a certain kind of acceleration happening, that acceleration is being caused by a force. So, since the direction is changing as the object is moving in a circle, in a circular path, so as an object moves in a circular path, it undergoes acceleration, and this acceleration it undergoes, that is what is referred to as centripetal acceleration. And from Newton's second law of motion, F is equals to ma, we know that this particular object, which is going around in a circle, has got a certain amount of mass. So it is not the mass which causes the acceleration. If you have acceleration, F is equals to ma from Newton's second law of motion, and you are going around in a circle, it is not your mass which is causing the acceleration, but that acceleration is being caused by a force. Are we clear? Whenever an object undergoes an acceleration, this particular object which is undergoing an acceleration has got mass. If the object is not accelerating, meaning that if the velocity of the object is not changing, even if an object has got mass, its acceleration is going to be equal to 0. So it's not the mass of the object which causes acceleration. However, when an object undergoes acceleration, meaning that either the size of the velocity or the direction of the velocity of this particular object is changing, there has to be a force which is causing that acceleration. Are we clear?
Yes, sir.
Whenever you have an acceleration, there has to be a force causing this acceleration. The force which is causing the acceleration is related to the acceleration and the mass of the object which is accelerating through Newton's second law of motion. F is equals to ma. So, if we have an object whose direction as it is moving around a circle is changing, then we have something called centripetal acceleration. Centripetal acceleration is the acceleration an object undergoes as a result of the change in direction as it's going through a circle. So if there is centripetal acceleration, then there must be centripetal force. There must be a force causing the acceleration. What I'm trying to say here is that when an object is moving in a circle, it's not doing so because it likes moving in a circle. Objects don't like moving in circles. Objects always like to move in a straight line. So if something is moving in a circle, it is because it is being forced to move in a circle. Are we clear? Whenever you see something moving in a circle, it's because that particular object moving in a circle is being forced to move in a circle. If you get your car, okay, then you go into a roundabout, then you decide not to turn, you lift your hands from the steering wheel, your car is not going to go in the roundabout. It will start moving in a straight line. It will get out of the roundabout. The reason why a car moves in a roundabout is because you have to continuously turn the car. You have to force the car to move in a roundabout. Otherwise, if you don't provide the force, then any particular object will prefer to move in a straight line. So naturally, any object prefers to move in a straight line. If there is nothing forcing it to stay in a straight line, an object is going to move in a straight line. That's why cars naturally, even if things are okay, if the alignment of the car is okay, if everything is okay, a car will always tend to move in a straight line, even if you lift your hands from the steering wheel, which is something I don't advise. Okay? But if you want your car to move in a circle, you have to force it. The same thing applies with anything else which moves in a circle. For example, our planet goes around the sun. Or if you have got something, as we are going to see during the course of this lecture, anything which is moving in a circle, there has to be a force. And this force, which keeps an object to move in a circle, that force is what is referred to as the centripetal force. So, this is what centripetal acceleration is. It is the acceleration which an object undergoes when an object is moving in a circle. And there is a way in which we work out centripetal acceleration. The centripetal acceleration is, as we are going to see during the course of the lecture, we work out the centripetal acceleration using this expression: AC, A for acceleration, C is for centripetal, is equals to V squared divided by R. So the velocity of the object in meters per second squared divided by R is going to give you your centripetal acceleration. But we also know that our V is related to how fast something is rotating. V is equals to R omega. So using that, if you substitute your V for R omega, as you will see during the lecture, you can also obtain your centripetal acceleration like this: R omega squared. So if this is acceleration, A is equals to V squared over R, then from this acceleration you can work out what the centripetal force is supposed to be. How much force do you need to provide for this particular object to have this kind of acceleration? Fc is the centripetal force. Fc is equals to, from Newton's second law of motion, you have the mass of the object, then you have whatever acceleration the object is undergoing. So in this case, your R omega squared is what you have here, and or you can write it like this: Fc is equals to m v squared of R. So that's basically what we have to discuss. Now, when it comes to centripetal acceleration, the other thing I will say is any force which is keeping an object to move in a circle is referred to as a centripetal force. So there are different types of forces which can act as centripetal forces. There are different types of forces, as we are going to see from the examples which you're going to look at, which can act as centripetal forces. So the other thing I want you to be aware of is that when we talk about centripetal force, we are not talking about a particular force, one kind of force. It can be different types of forces depending on the circumstances. I like to say that centripetal force has got many faces. It changes its face depending on what's going on. The kind of force which is going to act as a centripetal force depends on the circumstances which are being considered at that particular point. Okay, so centripetal acceleration, a point mass, basically a point mass is a small mass. If you've got a mass, sometimes it can be a small mass, sometimes it can be a very large mass. For example, our planet, which is very large. So if you've got a mass moving with a constant velocity v in a circle of radius r, like I've said, this particular object's mass is going to be undergoing an acceleration. The reason why it's undergoing acceleration is because its direction is changing. As much as the velocity v, the magnitude of the velocity v is the same, the direction of this particular object is continually changing. So if one part of the vector changes, then we say that the vector has changed. If the vector is changing, in this case, the vector we are looking at is the velocity, then we say that the particular object has undergone acceleration. So whenever an object is moving in a circle, that particular object is accelerating. The reason why it's accelerating is because the direction of that particular object is changing. And this acceleration is what we refer to as centripetal acceleration. The centripetal acceleration, most of the time, the centripetal acceleration, the object is accelerating towards the center of the circle. The object is always trying to get towards the center of the circle, most of the time. The centripetal acceleration, the object is trying to get towards the center of the circle. So the centripetal acceleration most of the time is directed towards the center of the circle. Sometimes it's not. Okay? Sometimes it's not, but most of the time it's directed towards the center of the circle. So the acceleration which an object undergoes as it's going through a circle, that's what is referred to as centripetal acceleration. And centripetal acceleration is just given by this particular formula here. We're not going to derive it. AC, which is the centripetal acceleration, is equal to v squared divided by r. The v is the velocity in meters per second, which is the linear velocity which this particular object is moving with. The r is the radius of the circle. Okay. Now, recall that we have a relationship between the velocity v and how fast that object is moving in a circle, which is the angular velocity. We know that we have shown in our previous classes that v is equals to r omega. So if we make this substitution for v equals to r omega, so we end up with AC is equals to v squared over r, where there is v here. If we substitute r omega like that, then squared, we end up with r squared omega squared. Then at the bottom divided by r. So one of these, r at the bottom, we cancel out one of the r's on top. Then you're going to end up with this. You're going to end up with r omega squared. So there are two ways, depending on what you have, what kind of information you've been given. There are two ways in which you can work out the centripetal acceleration. The centripetal acceleration AC, if you have been given the velocity in meters per second squared, then you know the radius of the circle. So AC is going to be equal to v squared divided by r, or if you know how fast the particular object is going round in a circle, which is what is referred to as the angular velocity, then you can work out the centripetal acceleration as r omega squared. Are we clear with this bit? These two ways of finding out the acceleration.
Yes, sir.
So now that we know the acceleration, then we have to recall from Newton's second law of motion is that whenever an object is undergoing an acceleration, it's because there is a force which is causing the acceleration. So when we use Newton's second law of motion, we can write the centripetal force, which is the force which is causing the acceleration. Okay? The centripetal force acting on this particular mass going round in a circle with radius, with velocity v, circle of radius r, the centripetal force Fc is going to be equal to the mass of that particular object times AC. There is nothing new about this bit. This bit is just Newton's second law of motion. F is equal to ma. But in our case, we have an expression of A, which is the centripetal acceleration. Two different expressions of A. So we can write our centripetal acceleration as being equal to m, which is the mass, multiplied by the acceleration, which is v squared of r, or we can write it as m multiplied by r omega squared. So this is how you work out your centripetal acceleration. Are we clear? The size of the... Yes. The other thing I want to bring to your attention, the thing I mentioned about centripetal force, to say, a force called centripetal force per se doesn't really exist. But this centripetal force is provided by other forces. In other words, centripetal force has got many faces, and it depends on what's going on. For example, if you have a car which is going round a roundabout, if your car is going round a roundabout, then the centripetal force in that case is the force of friction. If you have a car which is going round a roundabout, then the centripetal force in that case is the friction force. So in this case, the centripetal force is the friction force. So this Fc, which is equal to ma, is the friction force. So we write Fc is equal to the force of friction. Are we clear? Centripetal force has got many faces, depending on what's going on. Another simple case is in the instance where you've got a mass which is attached to the end of a rope. And this mass, you attach a mass to the end of a rope, like when you have got a simple pendulum. In a simple pendulum, you have a rope attached to some end. Then at the end of that rope, there is a mass you attach to a pendulum, and that mass is called a bob. I don't know if you did you do the pendulum experiment, the simple pendulum experiment, when you're doing your labs?
Yeah, we did.
You did?
Yes, we did.
Okay. So now, as your pendulum, as your simple pendulum is swinging, it's moving in a circular path. It's not a circle per se, but the path which a pendulum takes is part of a circular path.
Yes, sir.
Are we clear? So your pendulum is not moving in a straight line. No. Your pendulum is being forced to move in a straight line. It is being forced to move in a path which is part of a circle. And the reason why your pendulum is being forced to do that is because the rope you have attached to the pendulum is providing tension. Remember, your bob has got mass. Without that rope, your bob is going to fall to the ground because that particular bob has got mass, which means that it has got weight. Okay? But because of the rope you have attached to the pendulum, that rope you have attached to the pendulum is pulling the pendulum up. So when you're swinging, when it's swinging like that, the reason why it's swinging like that, going up and down like that, it's because of the tension which is in the rope. So the tension in the rope is forcing your bob to move in a circular track. So in this case, in such a case, when you have got objects attached to the end of a rope or objects attached to the end of a cable, and this particular object is, you start swinging it like the pendulum or whatever it is, or like, I don't know, some kind of, is on a swing or some kind of something you wear on top of you, or as a catapult, then the centripetal force is being provided by the tension. So in such a case, the centripetal force is the tension which is in the rope. Are we clear? Any question? The centripetal force is the tension which is in the rope. There are also other cases which are not very obvious. For example, we have our planet Earth and other planets going around the sun, but also I think you've heard of people sending satellites, launching satellites into space, and these satellites which have been launched into space, they go around the Earth. The reason why these satellites continuously go around the Earth is because there is a force of attraction between the Earth and these satellites. For example, the International Space Station goes around the Earth every 90 minutes. If you've heard of something called the International Space Station, it goes around the Earth every 90 minutes. Every 90 minutes, astronauts on ISS, they move around every 90 minutes to go around the Earth. So the International Space Station does that because there is a force of gravity which is pulling the station, provided by the Earth. Our planet goes around the sun all the time because it's being forced to move in a circular track. And the reason why that's the case is because our planet is being pulled by the sun. And all these other planets are being pulled by the sun, so that that's how we end up having this solar system. Okay. So in that case, in the case of things going around the Earth, for example, satellites or the moon, and also our planets going around the sun, the force of attraction, the centripetal force, is being provided by what is called gravity. So in this case, the centripetal force, Fc, is the force of gravity. There are other cases where you can have something being forced to move in a circle. So whenever you have got something being forced to move in a circle, then you have to look at what force could possibly be responsible for causing this particular object to move in a circle. Okay. So we have got an example. A 200-gram object is tied to the end of a cord and wheeled in a horizontal circle of radius 1.2 meters at a constant 3 revolutions per second. Assume that the cord is horizontal, i.e. that gravity can be neglected. So here we have a cord, you've got a mass attached to the end of a rope, and if you've got a rope, the reason why the rope is there is because the rope is going to provide tension. So the mass of the object is 200 grams, then the length of the rope, or the radius of the circular path, is 1.2 meters, and the velocity, or the angular velocity in this case, is 3 revolutions per second. So assume that the cord is horizontal. Sometimes that's what you're assuming, but physically, in reality, that's not always the case. So we're saying that you can neglect gravity in this case. Determine A, the acceleration of the object. Now, since this particular object is moving in a circle, the kind of acceleration we are talking about here is centripetal acceleration. I don't know what has happened here. Okay, but I think I'll need to edit these notes. So in this case, clearly there are some mistakes. The mass of the object, so the mass of the object is 200 grams. So that 200 grams is supposed to be 0.2 kgs. This says 2 meters, so that's not the case. So 0.2 kgs. I'll need to edit these notes after this class. Then the radius of the circular path is 1.2 meters. Then we can work out, we have got angular acceleration in revolutions per second. So this revolutions per second can be changed into radians per second. And when you do the change, you're going to end up with 18.8 radians per second. So with this, I'll put updated notes on this where I can make up these corrections. So in this case, so we have how fast the object is moving in a circle, which is 3 revolutions per second, but you do not do your calculations in revolutions per second. You have to do your calculations using radians per second. So you change your your angular velocity from revolutions per second to radians per second, which is 18.8 radians per second. So with this information, then you can work out what your centripetal acceleration is. Your centripetal acceleration AC is going to be equals to the radius multiplied by the angular velocity squared. So in this case, 1.2 meters multiplied by this bit, which is radians per second, and you get your acceleration as 442 meters per second. The one thing I want you to see, the one thing about centripetal acceleration I want you to see is that look at the revolutions, and I don't think this is very fast, and the radius, but you look at the resulting acceleration. The acceleration which comes out is very large. What I'm trying to say here is that when an object is moving in a circle, it's undergoing a lot of acceleration. The change in direction accounts for a lot in terms of acceleration. So this is our centripetal acceleration. With our centripetal acceleration like this, then we can find out the tension. What is the tension in the rope? Now the tension in the rope, as you have seen, the tension is what is providing the centripetal force. So we work out the centripetal force. Then after working out the centripetal force, that centripetal force is going to be equal to our tension. So Fc is equal to m multiplied by c by AC. So in this case, the mass of the object, which is 0.2 kgs, multiplied by the acceleration which we have, which is this, and we end up with a force of 85 newtons. So this is your centripetal force. But this centripetal force of 85 newtons is also the tension. Are we clear? So the tension in this case is what's providing the centripetal force. Is it clear?
Sir,
Yes?
if they could combine the friction force, so the way of found the tension force here to be 85 newtons. So if it were
The what?
the friction force,
Can you speak up?
if we were to find friction force instead of tension force,
If you have to find what?
so the way of that, if we were to find friction force,
Why are you finding friction force?
yes, it's going to have been the same the way you have done it to force in the code.
Yes. That's what we have up here. We have what situations where sometimes the friction force is what provides centripetal force. Other times it's the tension, Ft. Ft is what provides the centripetal force. Other times it's the force of gravity providing the centripetal force. They're just equal. That's why I said sometimes centripetal force has got many faces, depending on what situation is going on. Are we clear? So the centripetal force in this case, what is causing the object to move in a circle is the tension, and that tension is the centripetal force. Is that clear? Hello? Hmm?
Yes, yes.
Okay. Next example. What is the maximum speed at which a car can round a curve of radius 25 meters on level ground if the coefficient of static friction
Yes, sir.
between the tires and the rod is 0.8? Now, this example has got something very, very important. It's talking about maximum speed at which you can go around a curve. There are many examples when people have died because they were approaching a roundabout. And these people imagined that when you are approaching a roundabout, you can drive a roundabout at whatever speed you want. That's not how roundabouts work. Are we clear? Also, sometimes, roads are not very straight. Sometimes there is a cave. I think you have also heard of examples where people tell you, no, when you're driving on this road, there is this cave where people have accidents. The reason why people have accidents on a cave is because people don't understand that there is a maximum amount of speed with which you can drive a car on a cave. And usually when roads are being built, they'll put a speed limit to say, on this part of a cave, when a cave starts, when you're entering a cave, you must find a speed limit signpost telling you to say, on this part of the road, the speed limit is 70 kilometers per hour, or the speed limit is 80 kilometers per hour, or the speed limit is 90 kilometers per hour, or 60 kilometers per hour. The reason why that is so is because when you go beyond that speed limit, you cannot keep the car on the road. You will not be able to provide enough centripetal force. And that centripetal force is provided by the tires of your car. So engineers sit down, and when they're designing a road, depending on what surface the road is made up of, they will have from the surface of the road and an average of what kind of tires are likely to pass there. They will come up with a coefficient of friction. Say the coefficient of friction for a good car with good tires is supposed to be this much here. So engineers will come up with a coefficient of friction. From that coefficient of friction, then, and the curve, engineers will determine what is supposed to be the maximum speed with which a car is supposed to drive here. So if the maximum speed says 60 or 70, then you come driving your car at 100 kilometers per hour, then you're going to have an accident on that cave, because your car is not going to stay on that road. It's going to go off. Like I've said, a car likes moving in a straight line, and whenever a car is moving very fast, a car tends to move in a straight line. It's going to fight you very hard for you to keep it in a circle. So when you're approaching a cave, or when you're approaching a roundabout, the first thing you're supposed to do is you're supposed to slow down. Are we clear? Maybe you don't have a car right now, but in future if you have a car, when you approach a roundabout, you see the roundabout sign, and you're driving your car, you need to slow down. The reason why you need to slow down is because for you to go around that particular roundabout, your car needs to have a certain speed. The smaller the roundabout, the smaller the speed. The bigger the roundabout, the bigger the speed you can go around this roundabout. So if the roundabout is very big, then it means that you can drive at a faster speed. But if the roundabout is small, then it means that you can drive at a smaller speed. Okay, so let's see how that happens. So if a car is going to move a roundabout, there has to be a centripetal force, and that centripetal force is provided by friction. Fc, so Fc, the centripetal force Fc is going to be equals to the mass of the car multiplied by the velocity with which the car is going to move squared divided by the radius. So this is the centripetal force. This centripetal force, which is keeping all the cars which move around the roundabout, it's because of the friction between the tires of the car and the road. So the centripetal force is provided by friction. The force of friction, we know Fc is equals to the coefficient of friction multiplied by the normal force. So in this case, we are talking about whatever, I think this is supposed to be mu k. Since the car is going to be moving, it's not going to stop. We have got static friction when the car has stopped, but in this case, because the car is moving, we're going to have a coefficient of friction, like this case. So this is supposed to be changed to mu k. I'll do that. So this friction force, F is equals to mu k multiplied by Fn, that is what is providing the centripetal force. However, you also know from your studies when you're looking at Newton's second law of motion that the normal force Fn is equals to mg. The normal force is always equal to the weight of the car. Therefore, our friction force Ff is going to be equals to the coefficient of friction multiplied by the mass of the car multiplied by g. So this is your friction force. This friction force is equal to the centripetal force, what you have here. So when you make them equal, so Fc, which is the centripetal force, is equal to the friction force, which is Ff. So what we end up with is the following. We end up with the mass of the car moving it around the roundabout is multiplied by v squared divided by r is equals to mu s multiplied by m and g. Now something interesting happens. There is an m this side, which is the mass of the car. There is an m this side, which is also the mass of the car. When you cancel out the m's, then you remain with the following. You remain with v squared divided by r, which is equals to mu, which is the coefficient of friction, multiplied by g. This relationship where we are here, there is no mass here. This is a relationship of v squared divided by r, then mu, then g. There is no mass. What does that tell you? It tells you that the speed which we are interested in, the maximum speed in which with which this particular car is going to move around the roundabout does not depend on the size of the car. It doesn't matter whether you are driving a bicycle or you are cycling a bicycle, or you are driving a motorcycle, or you are driving a Vitz, or you are driving a taxi, a truck, or a bus. It doesn't matter. Because from this what we have here, you can see that mass is not important. Are we clear? There's no mass in this expression here where we are here. So the speed limit does not depend on the mass of the car. Whether it is a bicycle, it's a motorcycle, it's a Vitz, it's a Corolla, it's a truck, it's a bus, it doesn't matter. This speed limit has to be obeyed. So since you're looking for v, so you make v the subject of the formula, so you end up with v squared is equals to the coefficient of friction multiplied by g multiplied by r. Then this is v squared, so you end up v is going to be equal to the square root of the coefficient of friction multiplied by g multiplied by r. This is the expression which gives you the maximum velocity with which you can go around a roundabout. The velocity depends on the coefficient of friction. This coefficient of friction, the engineers will figure out what the coefficient of friction is. It also depends on g. We are on Earth, so g is known, 9.8 meters per second. But most importantly, the coefficient, this velocity depends on r, which is the radius of the circle or the radius of the roundabout. What this is telling you is that when r increases, then the velocity increases. The larger the r, the larger the velocity. So if a roundabout is bigger, it means that you can drive at a higher velocity on that particular roundabout. But if a roundabout is smaller, it means that you can drive only up to a certain amount of velocity. Are we clear? Okay. So that's what I have to say about roundabouts. The velocity, the maximum velocity with which you can go round a roundabout depends on the coefficient of friction. It depends on the acceleration due to gravity. It also depends on the radius. So if a roundabout is small, then the velocity is going to be smaller. If a roundabout is large, then the velocity is going to be larger. So in this case, when we substitute our things, the coefficient of friction have been given is 0.8, the acceleration due to gravity is 9.8 meters per second squared, and the radius is 25 meters. So you end up with a velocity which is approximately 14 meters per second. This relationship is very, very important. If the curve is small, if the curve is larger, if your curve is, that's why engineers, you see, when they're building a road, they try to make sure the curve is as large as possible, so that you can continue driving at a higher speed. If the road turns very suddenly, then you're going to have accidents. So the first thing to remember is, when you are approaching a roundabout, you have to slow down, because there is a certain amount of speed with which you can go around a roundabout. Okay. The other thing is, when you're driving, or when you start driving, you always have to look out for a speed limit. When the road tells you there might be no speed limit, sometimes the only sign which is there is that there is a curve coming up. When there is a curve coming up, there is always a certain maximum speed. So you always have to, first of all, you see a sign telling you there's a curve. Then after seeing the curve, there should be a sign telling you this is the speed with which you're supposed to drive in this curve. Make sure your speed of the car is below that speed limit, so that you can successfully go through that curve. Otherwise, if you try to drive at a speed which is higher than that speed limit, then your car is going to go out of the road. Then you end up with an accident. Okay. So that is on we have looked at centripetal force provided by tension. We have looked at centripetal force provided by friction. I don't know if you're going to manage this one. The other bit is centripetal force provided by gravity. Here, there's an example. A spaceship orbits the moon at a height of 20,000 meters. So this is basically probably a satellite, a spaceship, which is orbiting the moon. Assuming it to be subject only to the gravitational pull of the moon, find its speed and the time it takes for one orbit. For the moon, this is the mass of the moon. The mass of the moon is 7.34 times 10 to the power 22 kgs, and the radius of the moon is 1.738 times 10 to the power 6 radius. That's the radius of the moon. So if something is going around the moon at a height of 20,000 meters, then the orbital path, the orbit of the moon, of this spacecraft, the radius of the orbit of this spacecraft is a combination of the radius of the moon plus the height above the moon. So the radius of the orbit of the track of the craft is going to, which is capital R, is going to be equals to the radius of the moon, which is this, plus the height of the spacecraft above the moon. So this is what you have here. R is equals to small r plus h, which is height. So in this case, we end up with having r is equals to 1.738 times 10 to the power 6 plus 20,000, and this is what it gives us here. Not very much, but yeah, there's a small change here. The 3 changes, it becomes 5. Okay, so this is a radius. Now we know the radius. The next thing we are told is, yeah, we know the radius. We don't know the mass of the spacecraft. Usually the mass is not very important. However, we know the mass of the moon, which is that. Next, with that radius, we can find out the centripetal force of the spacecraft. The centripetal force of the spacecraft, Fc, is going to be equals to the mass of the spacecraft, which is the object which is moving in a circle, multiplied by the velocity of the spacecraft as it's moving in a circle, divided by the radius, like this. So this is the centripetal force. The centripetal force Fc is equals to the mass of the spacecraft divided by the velocity of the spacecraft as it's moving in a circle, then the radius of the circular orbit. However, this centripetal force, FC, is being provided, the spacecraft is going around the moon because it's being pulled by gravity. So the centripetal force is being provided by gravity in this case, which is Fg. And the force of gravity, Fg, is equals to capital G, which is the gravitational constant, multiplied by the mass of the spacecraft multiplied by the mass of the moon divided by the radius of from the center of the moon to where the spacecraft is. The G is what's known Newton's constant, gravitational constant. That's the value of G. The ms is the mass of the spacecraft. Then the mm is the mass of the moon. So this is our force of gravity, and it's this force of gravity which is providing the centripetal force Fc. So in that case, we equate our centripetal force Fc to our force of gravity Fg. So we have Fc equals to Fg. So our Fc, as you can see here, our Fc is equals to the mass of the spacecraft, the velocity of the spacecraft, and the radius of the circular orbit. So that's going to be ms v squared over r. Then our Fg is capital G ms mm divided by r squared. There is the mass of the spacecraft ms, and there is also the mass of the spacecraft this side. So when you cancel out the mass of the spacecraft, and also we cancel out this ms this side, we also cancel out the ms that side. There is an r here, there are two r's here, there's r squared here. So we cancel out one r here, we're going to remain with an r this side. So when you do that, we cancel out ms and an r here, we're going to remain with v squared is equals to G, the mass of the moon divided by r. So in this case also, so we end up with V is going to be equal to the square root of G, which is the gravitational constant, the mass of the moon, divided by the radius of the spacecraft's orbital path. Now, what does this show? As you can see, from this velocity, V is equal to the square root of G, the mass of the moon divided by R. Where is the physics here? What this shows you is that the mass of the spacecraft does not determine its speed. Are we clear? The speed of a spacecraft, whether it's a satellite or it's an international space station or anything, as a spacecraft is going around the planet or is going around the moon, the speed of the spacecraft does not depend on the size of the spacecraft. It depends on the size of the object the spacecraft is going around. It also depends on the radius of the orbital path. What you see, more importantly, is that the larger the object the spacecraft is going around, the higher the velocity. Are we clear on this bit?
Yes, sir.
Yeah. That's where the physics is. So if you're going to become an engineer, if you're going to change from medicine to engineering at some point, then you want to become an engineer, some stuff like that, you should know this, that when gravity is involved, when gravity is providing the centripetal force, then you're concerned about the velocity. The velocity does not really depend on the mass of the thing going in the circle. The velocity depends on the mass of the bigger object through which this particular object is going. So in this case, V is going to be equals to G. This is our G, the gravitational constant. Then the M, the mass of the moon, which is that, and this bit here is the radius of the orbit of the of the spacecraft. So if you do that, you end up with this velocity. V is equals to 1,669 meters per second. So this is the velocity in meters per second. So things move very fast in space, as you might have seen from the movies or whatever it is. Maybe the movies don't give you a very good impression, but the fact is, satellites and all these other things This is for the moon, and the moon is very small. Now you can imagine for the Earth, which is much, much larger than the moon. Here, velocity depends on the mass of the object. So if the Earth is much, much larger than the moon, it means that the crafts which are moving around the Earth are moving much, much faster compared to the ones which are moving around the moon. Are we clear? Maybe 5 times this. 5 times this velocity. Okay. So, how do we find out how fast this is? So we know this is the velocity meters per second, but how fast is this? How much is the angular velocity? So the angular velocity, we know angular velocity is equals to v. We know v is equals to r, which is the radius of the orbital path multiplied by omega. So from this, v is equals to r omega, we get this. Omega is equals to v divided by r. So we work out the angular velocity. So we end up with 1,669 meters per second divided by the radius. We end up with this as our angular velocity. That's how fast the craft is moving. Then, with this information, why do we need this? You must recall that at some point we had that relationship omega is equal to 2 pi r, 2 pi f. This omega is equals to, all right, omega is equals to 2 pi f, but f is equals to 1 over t. So we can find out how much time it takes the craft to go around in the moon once. So that's going to be the period. So the period is going to be equal to 2 pi divided by omega. So in that case, it's going to be our omega. That's what we have found here. Again, I think I'll need to rewrite this. Omega, that's what we have found here. Then, so our period t is going to be equals to 2 pi divided by our angular velocity, which is this, and we get this. We get 6,618 seconds. This 6,618 seconds, if you divide it into minutes, t is going to be 110.3 minutes. Basically, that's going to be 110 minutes 18 seconds. So basically, that's how fast this spacecraft goes around the moon. Are we clear? I will need to rewrite some of these so that it's very clear what's going on. Okay.
Scroll up on the question once more.
Sorry?
Scroll up on the question once more.
Okay. You want me to scroll up?
The question.
You have a question?
Yeah, the same question.
What about it? Which part have you not understood?
No, that, alright, I've seen. It's okay.
You have seen?
That's why I should have some.
Okay, fine. Okay, so we have to stop here. We're out of time. There is what's left. There is this example here. Is that there are other examples down there? Okay, there's other. I think the other examples probably, I don't know whether because we can try to look at them on Saturday and also start something else. So the remaining examples, I think, if we have to look at them, probably on Saturday, if it's necessary. But I think people can also just, from what you have done, you can see what's happening. Probably, yeah. Okay, we have to stop here. Unless people have got questions.
Sir, where is the link for Saturday class?
It's there on Moodle.
Okay.
Yeah, check for Group O Saturday. It's there on Moodle. I created a link some time back, which we could use for makeups. So there's going to be a makeup class on Saturday, and the link is there. So inform your friends so that they can join the Saturday class. Okay. So yeah, see you on Saturday.